Hello guys, welcome to another video. Today I would like to discuss about Apache Hudi, the theoretical part of Apache Hudi. I mean, what is Apache Hudi? How does it work? What is the architecture of Apache Hudi? What are the features of Apache Hudi? And why this table format has been very successful and all those things. Okay. And firstly, Apache source was developed in Uber and it is open sourced in 2016. From then on, other companies have adopted. Apache Hudi was widely used table format in many companies. And in AWS, Apache Hudi and Iceberg, both the table formats are widely used. This is just a theoretical video on Apache Hudi. I'll make another video where we can show you how do we create Apache Hudi tables from EMR, from Glue, and how do we create them and query them from Athena, all those things. This is just a theoretical video. And coming to the next slide, Apache Hudi is divided into five different layers, and the first layer is a lake storage, which is where the underneath Parquet or the Avro files will be stored. In our case, it can be S3 or ADLS or any GCP storage or any storage where we store the data in the Parquet or Avro format. That is called the lake storage, which is the cloud. And next is a open file formats, like Apache Hudi supports Parquet, ORC, Avro and H files, all these file formats. So you can store the data in all these four formats. And the next is the functionalities of Apache Hudis. One is the transaction database layer, then is the programming API and user interface. And the next is transaction database layer. This is the layer where Apache Hudi functionalities and everything will be explained. Like this is the layer where the concurrency, I mean, which I mean by like multiple writes and multiple reads can be handled. This is a layer in which the indexes can be handled. This is a layer in which the table services like cleaning, compaction and all those can be taken care. I'll explain you each and everything about what is table service, what is index, what is concurrency control, what is lake cache, what is meta server, everything in the coming slides. And the next is the programming API. This is where the reader and writers will be happening. And the next is the query engine. In our case, it can be BigQuery or Redshift or Athena or anything. As we have already saw, the first one is lake storage, which is nothing but the S3 or ADLS or whatever, where the data files or every Hudi files will be stored. Okay, that's the lake storage. We call it as a lake storage. And the next is file format. File formats is nothing but the way the Hudi stores the data. So if it is an merge on read, I mean there are two types of tables which we can create. One is merge on read and another is copy on write. In copy on write, we will just have the data files alone. But in the merge on read, we'll have the data files and the delta logs, which I'll tell you. But I mean the intention here is to explain the table formats or the file formats. So what happens in Apache Hudi is the data is split into partitions like other table formats also. Inside each partition, the data is again divided into file groups, and inside file groups, it is again divided into file slices. So for suppose if the table has 10 partitions, inside one partition, there will be file groups, and then it is a file slices. So in one file group, there can be multiple file slices and the multiple versions of the file slices. File slices is nothing but the part of the data. For suppose if you have inserted 5 rows today, and it will be stored inside the file slice, and if you write or if you update those 5 rows, a new file slice will be created. That's what it means. If you see here, Hudi operates on a logical structure of file groups and file slices, which consist of base files and log files. Base files are nothing but the Parquet files, and log files are nothing but the delta files, which means the transaction information will be stored, which means that if any update has happened, the updated related information, the latest updated information. If any delete has happened, the latest deleted row information. That kind of information we call it as log files. Base files is nothing but the data which we have inserted for the first time. I mean the fresh inserts, we call it as base files. So base files are compacted and optimized for reads and are augmented with log files for efficient append. So if you see, within each partition, the data is physically stored into base and log files. I've told you what is base file and log file, and are organized into logical concepts as file groups and file slices. File groups contains the multiple version of file slices and are split into multiple file slices. So inside one file group, there can be multiple file slices. So file slice is nothing but the actual data, and the file slice consists of base and log files if it is a merge on read table type. If it is a copy on write, it will just have the base files, there won't be any log files, because in copy on write the data will be rewritten. I'll explain you what is merge on read and copy on write, you don't get confused for now. So the intention is we need to understand how the data is stored. So partitions, the table will have multiple partitions. Inside multiple partitions it is aggregated into file groups, and inside file group it is aggregated into multiple file slices. So if you have written some inserts, they are called as file slices, and if you update or delete or something, a new file slice gets created for those 5 rows. So that's how the data will be stored. If you see, the file slice comprises of base and log files. Each file slice within the file group is uniquely identified by its commit timestamp. So each file slice is uniquely identified with the commit timestamp. I mean, when you have written the data, that timestamp will be logged, and each file slice is identified with its commit timestamp. So now if we go to the next slide, if you see, when you insert and update, this is the partition. Let's assume we have 10 partitions and we are taking one partition for explanation. And inside file slice we have multiple file groups, but here we have shown only one file group, and inside this file group we have file slice. So when you did an insert, this first one gets created, and again if you update or something, the second one gets created, and again if you further update, the next file slice gets created. It's nothing but the data only. File slice is nothing but the part of the data. And also every file group is identified with a unique ID. We call it as a file ID. File ID is very much important. I'll tell you why file ID is very much important. It helps in the updates and deletes. I'll tell you in the coming slides what is the purpose of file ID. But the file ID is nothing but a unique ID assigned to each file group. That's it. Inside the partition there can be multiple file groups, and inside each file group there can be multiple base files and log files. We'll have only base files if it is a copy on write table type, and if it is a merge on read table type, we'll have base files and log files. That's it. So now we need to understand what is the table services. So we understood what is the table formats, right? So the next is table services. As we have seen here, inside table services we have cleaning, compaction, clustering and indexing. So using these techniques in Hudi, we can query the table, or we can write into the table so quickly. These are the features which is helping, or which is uniquely representing Hudi to handle the huge amount of data, or the multiple writes, or the streaming data and everything. So if we go depth into each and every feature in table services, we'll get to know what it does. So inside that, see, if you see here, the table services in Apache Hudi are essential features designed to manage and optimize the performance and organize the data within Hudi tables. So these are the things which are helpful to optimize the performance of Hudi tables. I mean, if you want to query, or if you want to write, or if you want to do streaming writes or multiple writes, using these features only, Hudi is working like a perfect data lake. So the first one is clustering. So what does clustering means? So if you are querying a table on some keys, using clustering, it will reorder the data. I mean, it will reorder the data in the Parquet files as per the queries, so that the queries can be read faster. So clustering helps by organizing the data in a way that makes it faster to access. It does this by grouping the records that are often queried together, which is what I said. Like if you are querying the data on some keys or something, then it will rewrite the data accordingly, so that whenever you query next time, it can be read fastly. That's it. So that's what I said. This makes the queries more efficient because the related data is stored close together. For suppose if you are querying on some date column, so when you are querying on so and so date, and if it has all the data related to that date in one file group, it can be queried easily, right? So it is used to cluster these kind of scenarios, and also along with that, it will even do compaction as well. In the merge on read table types, we'll have the multiple data files and the log files, right? I mean, log files, what I said before is like it stores the transaction information, like what are the recent updates, recent deletes and all. So the so the merging of the log files and the data files is ideally done in compaction, but sometimes as it needs to reorder the data for efficient querying, even the clustering does that. Over time, a table might accumulate many small files. Clustering merges these into a larger file. If you have the multiple small files and multiple small partitions or multiple small file slices, it merges them into a single file slice as well. This is important because working with fewer large files is generally faster than dealing with many small files. That's it. So what it says is that the clustering is aware of other maintenance activities as well, like cleaning and compaction. I mean, cleaning is nothing but removing outdated files. If you have a data files which is being deleted from the table, and if you still have that data file, or if that file slice are in that partition, but we have deleted as per the transaction, it is no longer used. So the removing of those kind of files is called as a cleaning, and merging the small files into a single file is called compaction. So the clustering is aware of other maintaining activities like cleaning and compaction. For example, if a file group is already being clustered, the system might skip compaction and cleaning both if it has already being handled in clustering. That's it. And the next is compaction, which we have already saw. Compaction is nothing but the merging the small files into a single large file. Data changes like updates or deletes first recorded in the log files, or we call it as a delta files in the delta lake. Here we are calling it as a log files. The base files hold the bulk of actual data. Over time, having too many log files can slow down the query performance. So every time whenever you query, it has to read the data file and it has to read that log file, and it has to calculate whether this so and so record is updated, or if the so and so record is an old record, or if the so and so record is deleted or not. Every time it has to read both the log file as well as the log file as well as the data file. So it can be time taking. So to avoid that, Hudi internally does compaction as well. Compaction is nothing but the log file and the actual data file can be merged and made into a single data file. For example, if you have inserted 5 rows on day 1, on day 2 if you have deleted 3 rows, so when you query, it should result only the 2 rows which are not deleted. It should not return all 5 rows. So what it does is it reads the data file, it reads the delta or a log file, and it returns the 2 rows only. But what if you have hundreds of log files and hundreds of delta files? Every time it has to do all this calculation. To avoid that, Hudi can do the compaction as well. That's what this is. Over time, having too many log files can slow down the query performance because the system has to read multiple small files and merge them on a fly. Compaction is a process that merges these log files and a base file to create a new updated base file. Base file is nothing but the data file. That's it. So these are the two services, and we have indexing and cleaning as well. So cleaning is nothing but, for suppose if you have inserted a data today and it created a partition, and inside that partition the data is however divided into file groups and file slice. The actual data stores in the file slice only. So if you have deleted for suppose if you have a particular file slice as 10 rows, and if you have deleted if you have deleted those 10 rows in like one delete operation or multiple delete operation, let's assume the data is no more required, and it's waste of having that data in our S3 stored, right? So using this cleaning service in Hudi, which runs in the background, will clean that kind of unused data as well. See, let's read what they say. Cleaning is maintenance task in Apache Hudi that helps manage and optimize your data storage by removing old or unnecessary data files. This process ensures that your data lakes remains efficient, organized, and cost effective. This process happens incrementally, meaning it removes these files step by step as they become outdated. That's it. The primary goal is to free up storage space and reduce the cost, which keeps your data lake efficient and organized. So we don't need that outdated or unused data, right? So using cleaning, they will delete that file slice. The next thing is indexing. Indexing improves like how quickly we can query the data. For the read purpose, the indexing will be helpful. Like instead of reading all the partitions, we can directly read the specific partition based on the query. So which is happening because there is a thing called indices. So Apache Hudi stores indices. Indices are nothing but the column statistics, or the Bloom filter. Column statistics is nothing but the minimum maximum value in the each partitions, how many nulls present, all these kind of information. And the Bloom filter. Bloom filter helps to, it's a data structure which helps to directly find out the specific value in a specific partition instead of searching each and every partition. So these kind of indices will be stored in the indexing. So if you see this helps speed up the queries by focusing on relevant data and ignoring unnecessary partitions. So but there is a challenge here. The challenge is that updating these indices can slow down the process of writing new data, especially for large data sets, because when you have the huge amount of data, and there will be a lot of indices which needs to be updated. So which is going to cost us some. So due to solve this, Hudi updates the indices in the background, allowing data writing to continue without delays. So the data writing into the Hudi table and the updating indices will not be parallel, they will be asynchronous. We see the updating indices will be running in the background, so that it doesn't have to wait till that partition is written and all. The data gets written parallelly, and the updating of indices will be done parallelly. So that's indexing. So the next thing is concurrency control. Concurrency control on high level is nothing but Apache Hudi allows the multiple writers and the multiple readers to query or write into the table parallelly without blocking anything. So this parallel way of reading and writing into a table is called concurrency. If you see here, Apache Hudi coordinates how multiple users, writers, readers and service is nothing but the compaction, cleaning, clustering, all those things which we have seen here. These are all the table services, right? So access and update the tables and ensures no conflicts arises. So how is one of the ways how the concurrency is being controlled is because using the timestamp, because for every commit there will be a timestamp created, and that commit gets created with the timestamp. If you see the structure of the Hudi, if you see here, this commit happened with this so and so timestamp, this commit happened with so and so timestamp, and the status as well. It's we will discuss that as well. I'll show you how each commit has been created in the coming slides. So each action is logged with increasing timestamp, ensuring changes occur in a defined order. That's it. And also roles, the writers for updates, table service for compaction, readers for queries operate independently. Okay, that's one thing. And here for concurrency they use multi-version concurrence control, and this non-blocking concurrency control is still in the experimental stage. Along with this multi-version concurrence control, optimistic concurrence control, there is another method also, due to which we can have the concurrency in the tables. So in multi-version concurrency control, there won't be any blocker. For suppose if you are writing into a table and if you are reading from the same table, if at the same time in the same table, then it does not block you from reading. But in optimistic concurrency control, which is another mechanism to handle the concurrency, it blocks the for suppose if two systems are writing into the same table at the same time, if one system has come first to write, it blocks the other system, and the other system waits till the first system is completed. So that's the optimistic concurrency control, but we'll see more detail in the coming slides. So the next thing is lake cache, is nothing but in Apache Hudi, all the pre-merged file slices, I mean the file slices for which the base file and the log file is not merged, for those kind of files, it tries to store in the cache so that the reading or the querying of the table gets faster. It's still in the experimental stage. See what it says, lake cache addresses the challenges between writing speed and the query performance in data lakes. When writing data quickly, smaller files or deltas are created, but these may slow down the query execution. And so what it says is, if you see, the caching layer reduces the overhead of file opening and merging during queries, thus improves performance. So it keeps all those pre-merged file slices in memory so that it can read quickly. That's the lake cache. Now let's deep dive into another feature in Apache Hudi, which is timeline. So what exactly is a timeline? Timeline is nothing but the logging of all the actions performed on a table. It can be the commit, I mean the writing of data. It can be some table services like the cleaning or the compaction, or you can roll back the table into the previous version, right? The time travel is possible in all the data lakes. Tables like in Apache Hudi, in Iceberg, and in Delta. We can even roll back to the previous version. So whatever the action is performed on a table, that is being logged. That's called the timeline. If you see, Apache Hudi maintains a timeline which is a log of all actions performed on a table at a different instance of time. So how does these timelines are stored? These timelines are stored with these three combined. One is instant action, instant time, and the state. What is instant action? Is nothing but the actions which we are going to perform on a table, whether it is a commit, or whether it is a cleaning operation, whether it is a compaction, whether it is a rollback. So how are these timelines stored? The timelines are stored with the instant times stamp, the type of the action, and the state. So what are the actions? All which I have told, the commits, or the compaction, or the rollback, or the cleaning, everything what we have discussed. And the state. So first, when it started, it creates a timeline with the state as requested. Then it goes with the state as in flight while it is working on. So once the action is completed, I mean once the commit or a rollback it is completed, it's create a timeline with completed. So there are the three different states for each timeline. When the system, I mean when the table is requested with some kind of action, it creates with requested state. When the action is in progress, it creates a timestamp, it creates a timeline with in-flight state, and when the request is done, it creates the timeline with completed state. If you see here, so this is how, see the timestamp dot commit dot requested, timestamp dot in flight. So the timestamp dot completed will be the last one. So that's how the timeline. So timeline is nothing but the each and every operation which are being done on a table, and these all the operations will, I mean these all the actions which we perform on the table, whether it, I mean I'm naming it as an operation or action, whatever you call, so will be stored under the .hudi folder. And outside of that we'll have one is for metadata, and here is the Parquet files. That's how the structure of the tables will be stored. I'll show you in the next video with the demo by implementing that in EMR as well as in Athena. So that's what it says. The action type of the action performed on the table, the instant time, the current state of the action. So it stores the timestamp.action.state. What are the actions? It can be commits, cleans, delta commits. Delta commits means the small commits with the log files and the base file. Commits means it's a big file. I mean the complete inserts, or we can call it as a batch. And this is for streaming. We can call the compaction, rollback, all those. And these are the actions which I've said. And there are two types of timelines. So there are two types of timelines. Based on the timeline which we said, the recent actions will be under the Hudi folder, and all those which are under the Hudi folder are called the active timelines. And once the threshold has been reached, I mean we can configure that threshold timing in the configs for the Hudi table. All these timelines will be moved to this archive folder. So they are all the old timelines. If you see here, older timeline events are moved here after the threshold is reached to keep the active timeline efficient. So because if you keep all here only, it is difficult, or it's a costly operation to find out what is active action, what is the old action. So just to sort it out, they are moving the old timelines to the archive folder. That's it. So now you can ask me, what is the difference between the timeline and the delta log? So the timeline is just what is the action we have performed on a table, which explains what is the action we have performed on the table. But delta log will have the actual transformed data for a specific row. If you see here, it records the sequence of events, commits, compaction, cleanups in the life cycle of the Hudi table. The timeline helps manage data versioning and transaction history. But the delta log used in the merge on read tables, it stores the incremental changes, which are the updates or deletes, whatever we have. That's the difference between timeline and a delta log. And the next is a file layout, which we have seen above. The file layout is nothing but the way Hudi is storing our data, the actual data. So what happens is when you write into a table, there will be multiple partition. So in each partition, here we have for partition here, there can be multiple groups, file groups. Each file group will be assigned with one unique id, and inside each file group there can be multiple file slices. The base file and the log file in each file slice will be there, and if any update happens to this base file, it creates a new log file and a base file. That's how the file layout will be in the Apache Hudi table underneath. If we go through this context, the data table is organized in structured format in S3 ADLS, making it easy to manage and update data over time. So here is how it works. Each table is split into multiple partitions based on the certain key on the partition column, which is what they say. So within each partition, data is further divided into file groups, each with a unique file ID. So every file group will have a unique file ID. A file group contains several versions or slices. We call it as slices here. So inside each slice there will be a base file and a log file. This is typically a Parquet ORC file that holds the bulk of the data. So what is the log file? These contains the updates and inserts made after the base file is created. New data is written into these logs without modifying the base file directly. I mean, any updates or delete operations happened on a table will be stored in this log file. So as we have discussed before, Hudi uses MVCC, and during compaction, Hudi merges the log files and the base files into a new base file, and cleaning removes the old file slices. If for suppose if this got an update and we create a new base file and a log file, during compaction the base file and log file merges into one and becomes a one base file, and this is of no use, right? Because we already have created a new base file during compaction. So these can be deleted using the cleaning process, and all these cleaning, compaction, commits, everything will be logged using the Hudi timeline like here, and the older versions of these timelines will be moved to the archive folder. So the next thing is the table types. Hudi supports two types of table types. One is copy on write and merge on read. It just to explain you on high level, copy on write is nothing but when you write the data, first time it inserts and create the partitions and the file groups and the file slices, and when you update, it goes and find out the specific file slice and creates a completely new file slice. Instead of updating the whole partition, it just rewrites the specific file slice alone in the copy on write process or the copy on write table type. So that the Hudi, whenever you do the select statement on a table, it reads only the latest file slice alone. It ignores the previous file slice. There is no concept of log files in the copy on write. It's just only rewriting the file slice when you update a row in a specific file slice or in a partition inside a file slice. That's how the copy and write works. And the merge on read is where the log file comes into picture. So in merge on read file table types, for every update or a delete, a new log file gets created, and when you query the table, so Hudi internally will merge the data file and the log file and gives us the latest information. Every time when you query, it merges the latest log file and the data file and gives us the latest information. That's how the merge on read will work. So for streaming kind of purposes, we can go with the merge on read, and for copy on write, we can be used for the batch loads. And if you don't have any issue with the storage cost and all, we can go with the copy on write. And if you have the issue with the storage, we can go with the merge on write. So let's read this text. In Apache Hudi copy and write table, each commit generates a new file slice that includes the updated base file. This means that every update or insert replaces the existing data file with the new version in the columnar format. I mean, underneath the data can be stored in a Parquet or a ORC format, right? In Apache Hudi. So that's what Avro also. The table is implicitly compacted at every commit, ensuring that only the latest version of the data is present. So that when you do cleaning, the older version of the file slice will be gone and we'll have only the latest version. When updates occur, they don't modify the original data directly. Instead, a new file slice is created within the existing file group, which is what I have told. Like the new file slice gets created for the specific file slice, for the row in a specific file slice which we want to update. When a data is inserted, a new file group is created. However, the first time the new file group is created, when you update, the new file slice gets created. That's it. If you see the queries, first check the timeline for the most recent commit and use only the latest file slice only. This ensures that the queries operate on the most current committed data and not affected the partial writes or updates which are in progress. For suppose if we have some updates or if any writes are happening on a table, based on the timeline, it does not pick the data which is in progress, because if you recall what I have explained in the timeline, it for every commit we'll have the timestamp. What kind of commit is it a commit or is it a compaction or it is a cleaning and all, right? Like action, what kind of action, and then requested. So if it is in the requested or in the in-flight state, it does not read that kind of data. It reads only the data which is completed. So timestamp dot commit dot completed, only that kind of data it reads. So that's what this particular line says. And the next is merge on read. This is where the log file delta log file concept comes into picture. If you see, like copy on write table, Hudi stores the data in the base files, example parquet, within file groups. Additionally, for each file group, updates are stored in delta log file. These log files store the latest changes row by row. Periodically, Hudi compaction service merges these delta logs and a base files and creates a new base files. That's it. That's how the merge on read will work. And also there are multiple query types in Hudi. If you see, one is a read optimized query. This type of query only reads the base files, ignores the delta logs. It's fast but may not include the most recent data in the read optimized query. In the snapshot query, returns the most recent version of the data, merging the base files and the delta file. So if you go with the query type of snapshot, it merges the delta files and the actual data file and gives the most recent data. In the incremental types of queries, like it just fetches the data since a specific timestamp, like from the specific point in time onwards. This is same as incremental only, but it gives the befores and the later version of the data. If also any updates have happened, the previous version and the current version both can be fetched in the incremental query types. In the time tower queries, it helps to read the previous version of the data. That's it. These are the query types. And the table types which you have seen. The table types are copy on write and merge on read. In merge on read, we'll have the delta log concept, and copy on write just rewrites the specific file slice. And these are the different query types which we can do on a Hudi table. So as we have previously discussed in indexing there are different types of indices, right, which are helpful to query or to do the select statement on a table so quick. So that instead of reading all partitions, these indexes helps us to go and query the specific partition alone instead of reading all, so that we can avoid reading unwanted data. That's the one thing which we use indexes for. And also along with this, for the upsert statement, for suppose if any update is happening on a table, to find out the specific ID or a record key. I mean, in Hudi, we need to have the record key in our table. If we don't have the record key in our table from Hudi 1.0 onwards, it can by default create a unique UUID for each and every row in the table, so that it helps in updating the specific row quickly. Because when you can find out the specific file slice or a partition directly, you can avoid reading other partitions, and you can directly go and update those partition alone, right? So the indexes helps both in reading the data faster and in update statements as well, when you want to update something or delete something, so that it can directly go to the specific file slice or on. If you see here, ensures efficient handling of upserts by mapping a record key and a partition path to a specific file ID. So every file group will have a file ID. That is what we have discussed before. So inside every file group, there can be multiple file slices. So every file group will have one file ID. So using indexing, we can map a record key and a partition path to a specific file ID. So that record key and the path of that partition can be mapped to that file ID. So once the record is written to a file group, its mapping remains constant. So for suppose if student ID 1 is written into a specific file slice, and whenever you again update or delete, or you again write another row with this record key student ID equal to 1, it will write into that specific file slice only, or that specific file group only. It will not write in any other file group. That record key will goes to that specific file group only, always. how many updates or deletes you write, it just go to that specific file group only, and the data will be inside the file slice. So Hudi supports multi-model indexing, which allows a variety of indexing mechanisms using a metadata table. So all this indexing information will be stored in the metadata table only. And Hudi supports multiple indexing options. One is Bloom. Like Bloom is a data structure algorithm which is used to find out a specific key or a record key in that partition. Like using Bloom, we can this data structure algorithm, Bloom filter will help to find out where or in exactly which partition or in which file group that specific record key is available or present. So if you see, uses a Bloom filter, a probabilistic data structure that checks if a record exists in a file. It filters records by looking at the file level partition, making upsearch faster. And there is another thing called global Bloom, and the only difference is the record key should be unique in each partition level. If you see, a record key must be unique within each partition for if you in the Bloom index. And if you want to go with the global Bloom, the record key should be unique in the entire table. That's it. And the next type of indexing to find out the specific row or the specific record key is the simple and the global simple. This is nothing but just performs a join with the incoming row with the existing records, and just finds out the in which partition the specific record key exists. And the same as above, simple should have a record key must be unique within each partition in the simple indexing type. In the global simple, the record key must be unique across the table, across all partitions. And we can use a H-based indexing as well. If you use H-based indexing, it stores the index mappings in the external H-based table. We can use in-memory as well, and we have record index as well. So if you see, there are two types of indexes. One is global and one is non-global. Global is nothing but this global sample, global Bloom, all this called global indexes. That means the record key should be unique across all partitions. If you use non-global index, the record key should be unique across the specific partition alone. That's it. These are the different types of indexing, and using indexing we can just find out the specific record key or a unique key directly instead of reading the whole table. That's it. So now we'll go with the metadata table. So what is the metadata table in Hudi, and what does it stores? All the metadata information in the Hudi will be stored in this .hudi partition metadata in this folder. So what exactly is that metadata information being stored, and what is the use of that information, we'll find out in this slide. Here if you see, metadata table in Apache Hudi is an internal system designed to improve both reading and writing performance by efficiently managing and indexing table metadata. So the first thing what metadata tells is file listing. That means where exactly the so and so partitions are stored, where the exact information about all the files will be stored in the metadata table only. What is the advantage of having or storing it in the metadata table is, every time when you want to get the information about the files, you need to query that cloud S3 or ADLS and then fetch all the information, which is costly. So if you have that stored in a metadata table, you can just directly go and query that metadata table, and every day you don't have to list all the information. So metadata table gets updated after every insert and update periodically or asynchronously. So it replaces expensive file listing operations by proactively maintaining the list of data files, avoiding costly scan, especially in cloud environments like S3 or ADLS. So every time you don't have to scan the S3 or ADLS, and you can store that all the list of files, everything, where exactly it is stored, that information in the metadata table. And the next thing is, it helps in query optimization. How? By storing the column statistics like the minimum value, maximum value, or the number of nulls, null accepted columns. All these kind of statistical information for each and every column can be stored in the metadata table by storing column statistics and Bloom filters in a centralized indices. The metadata table acts as a centralized system. The metadata table enables faster query planning and execution, pruning irrelevant data more efficiently. We can avoid unwanted data. We can just read the partition which we need alone. So the next thing is multi-model indexing. This supports the metadata table supports multi-model index types such as the file level and the column level indices to handle various data access patterns. The next is ACID transaction. Metadata table support ACID transaction. What does that mean by is only if the file or the data is committed, then only that information will come into this metadata table. If any partition is partially written, that information will not come into the metadata table. That's why they are saying metadata table supports ACID. Only it's fully committed and fully written, then only that information comes into the metadata table. Metadata table will not have the partially written partition information. It supports the efficient lookups because it has all the indices information, right? So we can directly look up efficiently. If you see, it supports fast point based lookups, reducing the need to scan entire dataset. The metadata table utilizes the H file format to minimize the network calls and improve access times as well. So the metadata table currently provides this kind of entries. One is file indexes, tracks the file name, size, states, and speed up file listing, because it can speed up the file listing, right, instead of again querying the S3 or ADLS every time. And next is the column stats index, like column level statistical information, min, max, null, all this kind of information for each partition. And the next is Bloom filter, so that we can directly using the Bloom filter data structure algorithm, we can find out where the specific record key exists in which specific partition. And the next is record index, tracks record key location globally, enabling faster lookups across all partitions. And the next is how the flow happens in the Apache Hudi tables. Okay, so first any upsert comes, I mean any update or insert comes, in the initial stage we do the deduplication. If you see here, incoming records are first deduplicated. For suppose let's assume that there are 3 unique record keys coming, like with the same value as 1. If there are 3 coming, it deduplicates and sends only one record into the target based on the configuration value, like to take the latest or to take the earliest or all those things, which we will see in the practical video, which is our next video. So what happens is, the first is once we get the data, the deduplication happens, and once the deduplication is happened in the fly, then the indexing happens. So for this specific record key, for which file group I need to refer to, which file slice I need to refer to. So that kind of indexing will happen. Once the indexing is happening, then it decides on the storage, and then it writes into the specific partitions, and then it updates the indexes again based on what we have written. It again updates the indexes. So if you see, the incoming records are first deduplicated based on the user defined payload logic and pre-combined key. It is nothing but the record key. This ensures that only the latest version of the each record moves forward. For suppose that's what I said. If we have more than one unique keys in the incoming data, then it takes only one row only. It excludes all the duplicates. And the next is the index lookup. Hudi checks the indexes to see if the record exists and needs to update, or if a new record is for insertion. I mean, it checks the indexes and finds out whether it's a new record or it's an upsert stuff. And the next layer is where the layout optimization and the storage optimization takes place. This is nothing but like Hudi arranges the data in a way that reduces the duplication and minimizes the number of files being written and clusters similar data together. For suppose if you are partitioning based on city, and if it's a streaming job, we get data continuously. So it for that specific interval, it needs to arrange the data with the same city into a same partition or into the same file slice, so that the query retrieval and the upserts and everything will be faster. So that that optimization or the layout stuff will be taken care in this step, and then it writes into the target. If it is an update, it does the update. If it's insert, it creates a new file group. That's it. And then at the final stage, it updates the indexes again for the fresh data which we have received. And the next is the concurrency control, which we have seen before. Concurrency control is nothing but the Hudi allows to have the multiple reads and multiple writes to access the same table at the same time. How is that happening? That is happening because of the concurrency control only. Concurrency control ensures the coordination among different writers, readers, and background services. Background services are nothing but the table services, nothing but the clustering, cleaning, compaction, and all those things. Background services that manages the Hudi table. So it allows the multiple readers and writers and the background services to happen at the same time. Hudi guarantees atomic writes, meaning a write operation either fully succeeds or fails. Hudi won't read the or return the results when we query if a specific data is partially written, either write completely or nothing, because it supports the ACID. So there are two types of concurrency controls which Hudi supports. One is optimistic concurrency control, next is multi-version concurrency control. In optimistic concurrency control, for suppose if you are trying to write into the same partition or a same file slice, if multiple writers are trying to write into the same partition and the same file slice, then it will only allow only the one writer to write, and it blocks the other writers so that only one writer can write at a time. It logs the other writers. Once the first writer has done writing into the table, then the next writer will come into picture and it writes into the same file slice. If you see here, multiple writers are allowed to write into the table at the same time, but if they attempt to write to the same file or the same file slice or the same partition, conflict arises. Only one writer changes succeeded when conflict occurs. This model avoids blocking, and Hudi uses locks only for specific critical stages like committing and updates. That's what it says. And the next is MVCC. Here, this is lock free. So in the MVCC, it majorly works while you are querying. For suppose, if you are reading a table, if you are reading a specific data for which the write is also happening, then this MVCC makes sure that the partially written data is not being read in the select statement. If you see all the timelines, which we have seen before, the timeline, the action type, and the status. So if there is anything which is of in flight or started, then for those types it returns the result only if it is fully committed. So MVCC helps us to read only the fully committed data alone, not the partially committed data, in terms of or in the cases of streaming pipelines. And now we'll see what are the types of models we have in concurrency control. We have 4 different models, and the first is a simple one. We don't need any blocking or any locking or nothing of such. It's just a single writer with inline table service. Once the data will be written, and then the table services will takes place. Nothing but the compaction or cleaning or the clustering and all those things. If you see, no actual concurrency control is needed here. One writer and table services run inline after every write. I mean, table services will run after the write is happened successfully. Hudi uses multi-version concurrency control for snapshot isolation between writers and readers. So it uses MVCC so that it reads only the fully committed data alone. Partially written data will not be read when you read at the time when someone is writing into the same table. Ideal for simple use cases where there is no need for multiple concurrency writes. So, I mean, when there is no multiple concurrency writes, this model A will be so when there is no multiple concurrency writes, Hudi uses this model A, just a single write. If you see, the next one is almost same, but the table services are not inline. They are asynchronous. Single writer with asynchronous table services. That means it writes and immediately the table services will not be taken care. The table services will be asynchronous here. A single writer with asynchronous table services such as compaction, cleaning or clustering and all those things. Asynchronous table services run concurrently with injection without blocking the main writing process. MVCC ensures no conflicts between the writers and the table services. Using MVCC, it makes sure that there is no conflict between the writers and the table services. So the table services will be asynchronous. It's almost it's same as a model A. And the next one, which is for the real-time use cases, where is multiple writers. So allows multiple writers with optimistic concurrency control. As we have seen, for multiple writers, MVCC won't work. MVCC works only for the multiple readers or the writing and reading at the same time, and MVCC handles to read only the fully committed data alone, not the partially written data, that which can be taken care using the timeline concepts, because the timelines will have the action type and the status and everything, right? So if it is only completed, then only it reads that specific commit. So here, coming back to the multiple writers, allows multiple writers with optimistic concurrency control. External rocks are required to manage concurrency between the multiple ingestion writers or table servers, ensuring no conflicts when writing to the same file group. When writes overlap, only one succeeds. So what it says is, when there are multiple writers writing into the same table or same partition to a same slice, only one writer succeeds and the others writers will fail. Or else we can handle this using the locking mechanism. We can have external lockers like H-based locker and all those. There are different types of lockings which Hudi supports, using which we can make sure only one writer will be written and other writers will be logged, and once this first writer is released, the second writer will write into the same file slice. I mean, these concurrency controls will be applicable only if you write into the, only if multiple writers will write into the same file slice or the same file group. That's it. And this is in the experimental phase, non-blocking concurrency control. Where, so that's it guys, this is the theoretical concept about Hudi. What is Hudi, what are the concepts Hudi has, what are the things we need to know about Hudi, how are the writers and readers being handled, what is indexing in Hudi, what is concurrency control in Hudi, what is cache in Hudi, what are the services, table services which Hudi supports, what are the table types, merge on read and copy on write. These are the two table types which we have discussed, and how does the Hudi stores the data underneath, and all these things we have discussed. That's it. In the next video I'll show you how to create a Hudi table from EMR, from Athena, from Glue and all those things. That's it. Thank you so much for watching.